Today we're going to look at Chapter 18, Section B, on trigonometric ratios. Let's take a look again at a unit circle. I know we've seen this from Chapter 10, but here it is again. Remember that the unit circle has a radius of 1, that we measure the angle between the line OP and the positive x-axis, and that we, by convention, start at 0 degrees on the positive x-axis and go counterclockwise. And notice that we also give point P, which is any point on the unit circle, the coordinates x and y. Also, for any point on the unit circle, we can draw this triangle with point N on the x-axis, and we can label the leg parallel or on top of the x-axis x, and the leg of the triangle parallel with the y-axis as y. Therefore, for any point on the unit circle, cosine theta is going to equal the length of ON over the length of OP. And in this case, OP is always going to be the radius, and therefore is always going to be 1, and ON is always going to be the length x. So the cosine theta of any point, or of any angle for a point on the unit circle, is going to be equal to the x coordinate of that point. Likewise, the sine of that angle is going to equal the length of PN over the length of OP. And again, we're going to have y over the radius, which is 1, so that the sine of any angle for any point on the unit circle is going to be equal to y. This allows me to rewrite the coordinates of point P to cosine theta and sine theta. Also notice that because the radius of the unit circle is 1, the maximum value that we can have for x is 1, and the minimum value for x we can have is -1. So x always has to be between -1 and 1. Likewise, the maximum value for y is 1, and the minimum value for y is -1. So y also has to be between -1 and 1. So far, we've been considering measures of angle theta that are positive and go in the counterclockwise direction. This is the positive direction for theta. We can go in the opposite direction, though, clockwise. And this gets us a negative value for theta. So we're always going to start at the positive x-axis. If we go counterclockwise, we're going to have a positive angle. And if we go clockwise, we're going to have a negative angle for theta. Either is okay, and either can be plugged in to any of the equations that we're using. Let's take a look again at that unit circle, and more specifically the triangle that's formed by the radius, any point on the circle, and the x-axis. We know from geometry and Pythagorean theorem that x squared plus y squared is going to equal 1 squared in this case. That's a squared plus b squared equals c squared. But if we plug in the values that we found for x and y in the last slide, which are cosine and sine, we see that cosine squared plus sine squared of an angle is also 1. And we defined this in Chapter 10, but again, it's so important. We're going to redefine it here, and we're going to use it with radian measures as well. It's also worth mentioning that theta is positive for counterclockwise rotations, and that theta is negative for clockwise rotations. Let's take a look at a blank unit circle. If we draw a positive angle theta of 210 degrees and a negative angle phi of minus 150 degrees, we see that we're actually going to get to the same point. This is positive 210 degrees, and this is negative 150 degrees. In both cases, this little sliver of an angle right beneath the negative x-axis is going to be 30 degrees. So we can see that both of positive 210 and negative 150 get us to the same point P. We can also find the x and y coordinates of any point on the unit circle, any point P, if we know the angle theta that it forms with the positive x-axis. In this case, we'll call the angle 74, and we'll see that the coordinates of point P are cosine 74 degrees, sine 74 degrees. You'll notice if you plug in cosine 74 in your calculator, you get a positive value. That's because cosine's positive in this quadrant right here. You'll also notice that if you plug in cosine of 210 into your calculator, you'll get a negative value. And that's because cosine is negative in this quadrant. Let's take a look at where cosine, sine, and tangent are positive and negative in terms of the unit circle. Here's a somewhat silly diagram that will help us to remember where sine, cosine, and tangent are positive in terms of the four quadrants. Notice that we label the quadrants in counterclockwise order, starting with the first quadrant here, moving over to the second quadrant here, the third quadrant here, and the fourth quadrant here. The letters A, S, T, and C stand for all, sine, tangent, and cosine. And that means that in the first quadrant, all of the trig functions, sine, cosine, and tangent, are positive. In the second quadrant, only sine is positive. In the third quadrant, only tangent is positive. And in the fourth quadrant, only cosine is positive. You might be able to remember this better by remembering the silly little phrase, all silly turtles crawl. For our first example problem, we'll use a unit circle to find the cosine of 270 and the sine of 270 as well. First, let's draw the unit circle. Now, starting at the positive x-axis, we'll draw an angle all the way around to 270 degrees. And it turns out when we do this, we're going to hit exactly the negative y-axis. And because we know the radius of the unit circle is 1, we know the coordinates of this point. They are 0, negative 1. Therefore, the cosine of 270 equals the x-coordinate of that point, which is 0. And the sine of 270 equals the y-coordinate of that point, and that is negative 1. And you can verify that with your calculator if you want. In this example of problem, we're asked to find the possible exact values of sine theta when cosine theta equals 1/2. And again, we've done these problems in chapter 10, but it's good to review this because we'll be considering these problems in terms of radians soon. For this problem, we need to remember the important relationship that cosine squared theta plus sine squared theta equals 1. We're trying to find sine theta, but we know a value for cosine theta. The value for cosine theta is 1/2. So if we square that and add it to sine squared theta, we should get 1. Doing a little bit of algebra here, we see that 1/4 plus sine squared theta equals 1. Therefore, sine squared theta equals 3/4. Subtract 1/4 from both sides here. And then we can take the square root of both sides to find sine theta. And remember, when we take the square root, we need the positive and negative options. That's why we're finding all possible values here. So we're going to have the square root of 3 over the square root of 4, which is simply 2. We can illustrate the fact that there are two answers to this problem by using a unit circle. Remember that we were given cosine theta equals 1/2. So we go halfway between the origin and where the circle crosses the positive x-axis. And because that's our x value, cosine is our x value. But notice I can go above and below the x-axis here. So I actually have 2 points where cosine theta, or the x-coordinate, is 1/2. These are both positive values for the x-coordinate. Now in the first quadrant, we know that sine also has to be positive, so that's where the positive square root 3 over 2 would be placed, and that's the y-coordinate. In the fourth quadrant, the negative version of the sine would be placed, and that's the negative square root 3 over 2. And this is why we have 2 possible answers when we're given either a cosine or sine value. In a lot of problems, you'll be asked to find only one of these values. And again, we've done this in chapter 10, but now let's consider radians. Let's restrict theta to be between 0 and pi over 2. Well, we know from the beginning of this chapter that pi over 2 is equal to 90 degrees, so pi over 2 is up here and 0 is here. So if this condition has to be met, then only one of these values can be taken. And that's when we have to know where sine, cosine, tangent are positive and negative for each coordinate, or quadrant, sorry. So we know that theta between 0 and pi over 2 is the first quadrant up here. So I'm going to take the positive value of sine here. And so the answer would be positive square root 3 over 2. And the other answer would be thrown out for this particular problem if I was given that restriction.